Two research teams have studied the same California fault and come back with answers 11 times apart. One says the worst it can do is a magnitude 6.5. The other says 7.2, nearly 19 feet of ground moving sideways at once. Nobody has settled it because the fault runs through country where you cannot put instruments. On Wednesday, it produced two earthquakes 59 seconds apart in the one section neither model covers. By the end of this, you will know which answer the evidence now points to, and why that is not good news. On Wednesday afternoon at 20 minutes and 58 seconds past 3 Pacific Time, the ground moved about 19 miles northwest of a small town in Mendocino County called Covelo. The United States Geological Survey logged it as a magnitude 4.1 at a depth of 4.8 miles. That alone would not have been news. Northern California produces earthquakes that size regularly, and this one happened in country so empty that almost nobody was close enough to notice. 59 seconds later, it happened again, and it was bigger. A magnitude 4.5, roughly 19 miles northwest of the same town at a depth of 2.8 miles. The Geological Survey filed it under event identifier NC754121157, and a seismologist reviewed the solution by hand rather than leaving it to the automatic system. That detail matters because the numbers you are hearing are not a first-pass computer estimate. Somebody checked them. Those two events were not the beginning. The Redwood Coast Tsunami Work Group, the regional preparedness organization covering California's north coast, assembled the sequence and found it had started the previous evening, a magnitude 4.0 on Tuesday at 25 minutes past 5 on the same patch of ground. So, the full sequence is 3 moderate earthquakes across roughly 22 hours in a place with no towns, no meaningful road network, and very little seismic instrumentation. The shaking went a long way. The largest event was felt from Colusa out in the Sacramento Valley all the way to Arcata on the Humboldt coast, about 200 miles, with reports from Fortuna, Eureka, and McKinleyville. Nobody was hurt and nothing was damaged. The epicenters sit in the mountains east of Island Mountain, where the Humboldt, Trinity, and Mendocino County lines converge on ground that is almost entirely national forest and private timberland. 200 miles of felt shaking from a magnitude 4.5 is not normal, and the reason is the depth. At 2.8 miles down, that earthquake was extraordinarily shallow, which concentrates energy near the top of the crust instead of spreading it through miles of rock on the way up. It also means the same geometry applied to a much larger earthquake on the same patch of ground would be unusually destructive for its size. There is one more thing about that depth. Both of these earthquakes happened inside the exact interval that is the single most contested parameter in the published science on the fault they occurred on. The structure underneath all of this is the Bartlett Springs Fault Zone, and if you have never heard of it, that is not an accident of your education. It is one of the 3 main branches of the San Andreas system north of San Francisco Bay. The San Andreas itself runs along the coast. The Mahakama Fault Zone runs in the middle. The Bartlett Springs runs farthest inland, carrying a share of the Pacific Plate's northwest motion that the San Andreas does not. It is by a wide margin the least studied of the 3. And there is no earthquake anywhere in the written record that can confidently be pinned on it. Physically, it is a right lateral strike-slip fault, meaning the two sides slide past each other horizontally. Its published length depends entirely on which strands you count: 170 kilometers in one assessment, 120 in the most detailed recent study, 85 in one national hazard model. Those are not small differences, and they are the first sign of how thin the ground is here. The geometry is not self-contained either. The active trace runs southeast from north of Round Valley down to the eastern side of Clear Lake, where it steps right by about 2.5 kilometers onto the Hunting Creek Fault. Southeast of that is the Berryessa Fault, generally considered the northern end of the Green Valley Fault. Follow that chain far enough, and you are in the eastern San Francisco Bay Area. This is not an isolated fault in the woods. It is the northern end of a continuous line of structures running down into one of the most populated regions in the country. Then there is the slip rate, and this is where the published record stops agreeing with itself. Geodetic measurements put it between 4 and 8 millimeters per year. The most rigorous estimate from Bayesian modeling by Murray and colleagues in 2014 gives 7.5 below 13 kilometers. And the seismologist Ross Stein, writing for Temblor, puts the long-term rate at 1 to 2 millimeters per year. The peer-reviewed study of this fault sums it up in 5 words. Its slip rate is poorly known. A fault whose loading rate is uncertain by nearly a factor of 9 is a fault whose earthquake budget nobody can balance. That uncertainty is about to become the whole problem. Here is what makes the Bartlett Springs Fault genuinely unusual among California faults. 2 respected research groups have built 2 models of how it behaves below the surface, and they disagree. Not slightly, but fundamentally. Because they disagree, they produce 2 completely different worst-case earthquakes. The first model, from Leenkemper and colleagues in 2014, says the fault is locked from the surface down to 10 or 11 kilometers. Locked means stuck. The 2 sides are not sliding. Strain is accumulating, and eventually all of that stored motion has to come out at once. When Lozos and colleagues ran the numbers on that geometry in 2015, they got a maximum magnitude of 7 to 7.2 with horizontal slip of 5.6 to 5.8 meters, a fault moving nearly 19 feet sideways in a single event. The second model, from Murray and colleagues in the same year, says something almost opposite. The fault is creeping everywhere below 5 kilometers. A creeping fault slides continuously and quietly, releasing its motion a fraction of a millimeter at a time instead of storing it for one violent afternoon. If most of the fault is creeping, there is far less energy available, and the maximum event drops to a magnitude 6.5 to 6.7 with about 1.6 meters of slip. Consider what separates those answers. A magnitude 7.2 releases roughly 11 times the radiated energy of a magnitude 6.5 and produces about 3.5 times as much slip. One is a serious regional earthquake that damages towns across the Coast Ranges. The other is a generational disaster for the interior of Northern California. The entire difference comes down to one question: how much of this fault is greased, and how far down does the grease go? Until recently, there was no good way to answer it because the fault runs through terrain where you simply cannot put instruments. In 2024, a team led by Victoria Langenheim published a study in the journal Geosphere that attacked the problem from a different direction. If you cannot measure whether the fault is sliding, measure what the fault is made of and work out from the rock itself where it has to be slippery. The rock in question is serpentinite, a metamorphosed ultramafic rock, greenish, waxy, and mechanically weak. Laboratory work by Moore and Lochner in 2013 showed that where serpentinite meets ordinary crustal rocks, chemical reactions along that contact significantly reduce friction and stabilize the sliding. In plain terms, serpentinite is nature's grease. Where you find it in a fault, you tend to find creep instead of earthquakes. It has one other property that makes this approach possible. It is strongly magnetic. Even if you cannot walk into the terrain, you can fly over it and map the rock from the air. So that is what they did. The team modeled aeromagnetic and gravity anomalies along 14 cross-sections spanning 120 kilometers of the fault zone, folding in more than 5,800 gravity measurements. The work was funded by the Geological Survey and by Pacific Gas and Electric Company, which will matter a great deal later in the story. What they found on 13 of the 14 profiles was more serpentinite at depth than the surface geology predicted. There is more grease down there than anyone assumed, and if serpentinite predicts creep, then much of the Bartlett Springs Fault is creeping, particularly along the central and southern sections where the modeled serpentinite extends 10 kilometers below the surface or further, which means the study came down on the side of the Murray model. More creep. Lower maximum magnitude. In the author's own careful language, the results suggest a possible reduction in the maximum amount of slip from a single earthquake rupture on the fault zone. If you stopped reading there, you would close the paper, feeling better about this fault than when you opened it. Almost nobody stops reading there, and the last two findings are the reason. The first is that the pattern breaks at the north end of the fault. The study's own words are worth quoting precisely because the precision is the point. The northernmost two profiles, they wrote, suggest that the serpentinite is restricted to the upper 1 kilometer, or mostly southwest of the fault zone, in contrast to the rest of the models. Read that again with the mechanics in mind. Everywhere else along the fault, the grease extends far below the surface and the fault can slide. At the northern end, either it is confined to the top kilometer, leaving everything underneath ungreased, or it sits off to the side of the fault entirely, where it does no good at all. The argument for a lower maximum magnitude is an argument about the central and southern sections. The northern end does not appear to qualify. The second finding is one sentence long, and it is stated flatly. We do not extend our analysis north of Round Valley. That is the edge of the map. The best modern characterization of this fault's slipperiness has a hard northern boundary, and beyond it, nobody has done the work. Now put the earthquakes back on that map. Covelo sits in Round Valley. The events of Tuesday and Wednesday struck roughly 19 miles north-northwest of Covelo, at or beyond the northern limit of the study area, in the one section of the fault where the serpentinite model does not predict pervasive creep. This is why the sequence matters more than 3 moderate earthquakes in an empty forest should. The reassuring conclusion about this fault, greasier than we thought, less dangerous than we feared, was drawn from profiles 3 through 14. The ground that just moved 3 times in a day is not covered by it. It is in the gap. Gaps of this kind have a specific mechanical significance. If the northern section is locked while the central and southern sections creep, the fault has a boundary inside it, a place where sliding rock meets stuck rock. On strike-slip faults, those boundaries are exactly where ruptures tend to nucleate and exactly where they tend to stop. There is a geometric complication right there, too. The geosphere team documented that, at Round Valley, the old right-stepping geometry appears to have been abandoned, with the active trace now making a left compressional step as it enters the basin. A compressional step is an obstacle, a place where the fault has to squeeze rather than slide, and obstacles concentrate stress. The earthquakes happened at the north end of exactly that structure. There is a counter-argument, and it deserves a fair hearing because it comes from the same study. Creeping faults are not silent. They produce small earthquakes routinely, and the accepted explanation is that a fault which is mostly sliding still contains small stuck patches, knots of stronger rock embedded in the weak material. Those knots resist until they fail. And when they fail, they produce an earthquake. The geosphere team even found a correlation between where they modeled serpentinite and where microearthquakes occur. And they did not use seismicity to build the models, so that correlation is independent evidence. Small earthquakes on this fault are therefore expected. They are the signature of a creeping fault working normally. The problem is the size. That framework predicts earthquakes below magnitude 3. What happened on Tuesday and Wednesday was a 4.0, a 4.1, and a 4.5. That is 1 to 1.5 magnitude units above the expected signature. And because the scale is logarithmic, the gap is larger than it sounds, somewhere between 30 and 200 times more radiated energy per event than a magnitude 3 would produce. That does not make these earthquakes anomalous in any absolute sense. Moderate earthquakes happen on all kinds of faults, and nothing here breaks physics. What it means is narrower. These events sit above the size range that the creeping fault explanation comfortably absorbs as background noise. The shape of the sequence points the same way. In a standard main shock and aftershock sequence, the biggest event comes first, and everything afterward decays. This did the opposite: 4.0, then 4.1, then 4.5, with the largest event last and smaller events threaded in between. That is a swarm, and swarms are typically driven by something other than one patch. Releasing stress, usually fluid moving through rock, or slow slip loading a series of small patches one after another. Swarms are not new on this fault system, but the size of these ones is. And one detail resists tidy explanation. The second earthquake was both larger and shallower than the first. It stepped up toward the surface and got stronger 59 seconds later. If the Bartlett Springs Fault has never produced a large earthquake in the historical record, it is fair to ask why anyone should be nervous about it. The answer is buried in a trench, and it is the most important fact in the story. In 1986, and again in 1991, researchers named Taylor and Swan excavated across the Bartlett Springs Fault and read the layers. They found evidence of at least 3 prehistoric earthquakes, the most recent of them somewhere between 300 and 1,000 years ago. The interpretive weight comes from a threshold Ross Stein stated plainly. To be seen in a trench, he wrote, a rupture usually needs to be larger than magnitude 7. A paleoseismic trench records surface rupture, the moment a fault breaks all the way through the ground and offsets the soil layers. Earthquakes that never reach the surface leave nothing behind to dig up. So, 3 events in a trench most plausibly means 3 earthquakes at or above magnitude 7 on this fault, the most recent landing somewhere between roughly the year 1026 and the year 1726. That resolves the apparent paradox, and the distinction is worth being careful about. This fault has produced large earthquakes. It has simply not produced one. During the roughly 175 years, California has been writing things down. Hasn't broken in recorded history is accurate. Has never broken is false. The gap between those two statements is the entire hazard. Stein's own conclusion, written before any of this week's activity, reads, although fortunately remote, this fault is potentially dangerous. The arithmetic of when it might do it again refuses to settle. For the same reason, nothing else here settles. If the fault moves 1.5 millimeters per year, 3 meters of slip takes about 2,000 years to accumulate, and the fault is early in its cycle. If the 7.5 millimeter figure is right, the same 3 meters accumulates in about 400 years, which puts this fault at or past the elapsed time since its last event. Both readings come straight out of the published numbers. There is an obvious objection to everything above. The newest science says most of this fault creeps. Creeping faults do not produce catastrophic earthquakes. So why worry? The answer to that objection happened 6 weeks ago, 40 miles away. On the 24th of June, at around 8:15 in the morning, a magnitude 5.6 struck Redwood Valley, about 9 miles north of Ukiah. It cracked structures. It caved in roofs. At the peak of the outage, 10,000 Pacific Gas and Electric customers lost power, and the Mendocino County Executive Office reported injuries, though no deaths. Amy Williamson, a research scientist at the UC Berkeley Seismology Lab, called it the largest earthquake on the Macama Fault in 75 years. Here is why that event is the load-bearing counterexample. The Macama Fault creeps, not theoretically, not by inference from rock chemistry, but measurably. Alignment arrays put surface creep at more than 4 millimeters per year near Ukiah and Willits. It is the neighboring branch of the same regional system, running about 110 miles from Healdsburg up to Laytonville. It is an extension of the Hayward Fault system. It is a documented, instrumented, actively creeping fault. And in June, it produced an earthquake that damaged buildings and injured people. Creep does not mean safety. At most, it means the maximum plausible event may be smaller than the fault's raw length would suggest, and even that is contested. The geosphere authors say so directly. The role of fault creep in reducing the magnitude of large earthquakes is, in their words, the subject of debate. So the sentence, "The Bartlett Springs fault creeps, therefore it is fine," is not a conclusion anyone is entitled to. The fault next door creeps, and it hurt people in June. Line up the last 6 weeks, and the pattern gets harder to wave off. June 24th, the 5.6 on the Mayakama near Ukiah. July 10th, a magnitude 4.1 on the Bartlett Springs Trace. July 28th, a 4.3 on the Macama near Cloverdale, inside a sequence that kept producing events into early August. We covered that swarm on this channel as it was building. And now Tuesday and Wednesday, the Bartlett Springs cluster. 3 distinct segments of one regional fault system, active in turn over 6 weeks. None of that establishes a causal chain. Faults 40 miles apart do not straightforwardly trigger each other, and static stress transfer falls off roughly as the inverse cube of distance, which kills that idea fast. But what it establishes is that the Coast Ranges system north of the bay is doing more than its baseline right now. Everything you have heard about this fault's prehistoric ruptures, its slip rate, its serpentinite, and its maximum magnitude exists for one reason, and it is not scientific curiosity. Scott Dam sits nearly on top of the Bartlett Springs fault zone. It impounds Lake Pillsbury, and it is one of 2 dams in Pacific Gas and Electric's Potter Valley project, the other being Cape Horn Dam downstream. A utility built a concrete structure holding back a reservoir almost directly above a fault line that some models say can produce a magnitude 7. So, the utility needed to know what that fault could do. The 1986 trench study, the one that found 3 prehistoric ruptures and gave us the only long-term record this fault has, was not a curiosity-driven research project. It was a final report by Geomatrix Consultants commissioned by Pacific Gas and Electric, and its formal title describes a geological assessment of the seismic potential of the Bartlett Springs shear zone for Scott Dam. The 2024 serpentinite study was likewise supported in part by the same company. Every significant thing we know about the danger of this fault, we know because something valuable was built on it. The utility's behavior suggests it takes the answer seriously. Pacific Gas and Electric has lowered the reservoir level at Lake Pillsbury in recent years, specifically to reduce loading. Not a press release, but a physical action with a real operational cost, taken because the operator treats the seismic risk as concrete rather than theoretical. The company has also filed a surrender application and decommissioning plan with federal regulators, moving toward eventual removal of both dams. The stated primary reason is economic, but seismic issues have also been cited, and Lake County officials have publicly challenged that reasoning. Which brings us to the theory circulating online, and it deserves a straight answer rather than a dismissal, because its factual core is unusually solid. The claim is that the dam is coming out because somebody knows the fault is about to go. The pieces are real, The reservoir was lowered. Seismic issues were cited. The dam is being decommissioned. But federal surrender proceedings run for years through a regulatory process. They are not an emergency response to a specific imminent earthquake, and no such earthquake has been forecast by anyone. The truth underneath the theory is more interesting than the theory. This fault's danger was never a secret. It is documented in reports a utility paid for and summarized by a seismologist who used the phrase potentially dangerous in public. The same answer applies to the broader suspicion that somebody is sitting on bad news here. The most alarming assessments of this fault are the published ones. What is actually true is narrower, and in its way, worse. This fault is understudied not because anyone suppressed the work, but because it runs through steep, remote, heavily forested terrain where almost nobody lives, and hazard research funding follows population and infrastructure. The honest version of the suspicion is not that they are hiding it. It is that nobody was looking because nobody lives there. Start with the base rate, because it is the most likely outcome by a wide margin. Globally, the fraction of moderate earthquakes followed within days by a substantially larger event on the same structure is a few percent. A magnitude 4.5 is overwhelmingly likely to be the largest event of its sequence. The energy released in this cluster is trivial against the fault's capacity. The 4.5 alone is about 1/16,000th of a magnitude 7. Nothing this week relieved any meaningful strain. Whatever is loaded is still loaded. The specific thing to watch is location, not magnitude. The July 10th event struck about 18 miles along strike from this week's cluster. If a third cluster appears further northwest toward the northern end of Round Valley and the transition below the Mendocino Triple Junction, where the San Andreas system hands off to the Cascadia subduction zone, that is genuine along-strike migration on a section of fault whose behavior is unmapped, and it would change how this sequence reads. If the activity fades in place over the coming days, it was a stuck patch letting go, and nothing more. The second thing to watch is whether anyone extends the mapping. The 2024 study drew a hard northern boundary at Round Valley and said so in writing. The ground that just produced 3 magnitude 4 class earthquakes lies at or beyond that line. Whether the aeromagnetic modeling gets carried north into that gap, and what it finds when it does, is the single measurement that would most change the hazard picture here. Right now, the honest position on the northern Bartlett Springs fault is not that it is dangerous or that it is safe. It is that nobody has looked. The third thing runs on a longer clock. If the decommissioning completes and the dams come out, the legal obligation that drove almost all of the research on this fault goes with them. When the dam is gone, so is the reason anyone was required to care. What we are left with is a fault at least 120 kilometers long, running from north of Round Valley, down through Clear Lake, and onward toward the Eastern Bay Area. A dam sitting nearly on top of it, with its reservoir deliberately lowered. 3 prehistoric earthquakes recorded in a trench, the most recent within the last 1,000 years. A slip rate nobody can pin down within a factor of 9. And on Wednesday afternoon, 2 earthquakes 59 seconds apart, less than 3 miles below the surface, in the one section of this fault that the newest and best science does not cover. We will know more if the sequence migrates, and we will know more if somebody flies the northern profiles. Until one of those happens, the accurate statement about the Bartlett Springs fault is the uncomfortable one. This is a structure that has broken at magnitude 7 at least 3 times, in a place where the measurements that would tell us whether it is ready to do it again have simply never been made.